Previously, we learned about proofs using segments. Today, we'll learn about proofs using angles. Let's begin by reviewing some concepts. Determine whether the statements are valid or are invalid. Statement 1, AB equals CD. This statement is invalid. The reason it's invalid is because there are line segments, or I should say segment notation above these segments, and when we express equality, we don't use the line segments. Statement 2, AB is congruent to CD, and this is valid, and that's exactly how you should write it. When we have congruency symbols, we'll also have the notation above the segments. Statement 3, AB is congruent to CD. This statement is invalid, and the reason it's invalid is because it does not have the line segment symbology above it. Statement number 4, angle 1 equals angle 2. When we state equality with angles, we need to write the measure of angle 1 equals the measure of angle 2. Statement 5, the measure of angle 1 equals the measure of angle 2, and that is valid. And last, number 6, the measure of angle 1 is congruent to the measure of angle 2. This is invalid. The reason that it's invalid is this is congruency, so we do not state measure. It will just say angle 1 is congruent to angle 2. To be sure to have something like that in your notes. Let's move on. The proofs in this section have the same general approach as those in the last section, but we'll be proving angles, not segments. In the last section, we were changing between equal and congruent statements. In this section, we'll move back and forth between the angles measures and mathematical operations. Let's begin with our first theorem. You should have paper with something to write with out and record your theorems, and whenever possible, record the pictures that are next to them. So, theorem 2.7.1. Angle congruence is an equivalence relation. Whenever we state congruence, we will have an equivalence relation theorem to go with it. Theorem 2.7.2, the adjacent angle sum theorem. If each of two adjacent angles is congruent to another angle in a second pair of adjacent angles. So, if each of two adjacent angles, so here are two adjacent angles, is congruent to a second pair of adjacent angles, here's our second pair, then the larger angles formed are congruent. So this larger angle on the outside will also be congruent. Whenever a new theorem is presented, we need to make sure that we verify the definitions that are contained in the theorem. The definition adjacent means coplanar angles with a common side but no common interior points. So the common side in this interior of these two angles is right here. So once again, angles with a common side but no common interior points are adjacent angles. This theorem allows us to add those angles together. So let's go ahead and break down our adjacent angle sum theorem. In your book, you have some pictures next to these angles. What you should be doing is drawing whatever is in the given into the pictures. So as an example, it says angle 1 is congruent to angle 3. So in this we have an angle 1 and we have an angle 3, and we know they're congruent, so we will make one arc in this angle to show that they are congruent to each other. We also know that angle 2 is congruent to angle 4. So this is angle 2 and this is angle 4, and we'll go ahead and we'll use two arcs to show that they are congruent. Now you're given some more points and other information, so you should add that to your drawing. Point C, we have a vertex of point B, this ray is BA, and this ray is BD, and on the next angle we have this point R, the vertex of Q, and ray QP, and we also have ray QS. So these are all the notations you have so far for these angles. What we're going to prove is that angle ABC is congruent to angle PQR. Moving on, we'll now start filling in our proof. So we have given angle 1 is congruent to angle 3, and angle 2 is congruent to angle 4. And you see that under your first statement, and that is the given, and that is your first reason. In our second step, we now have the measure of angle 1 equals the measure of angle 3. So the measure of angle 1 equals the measure of angle 3, and the measure of angle 2 equals the measure of angle 4. We can reason this by using the definition of congruent angles. If they're congruent, their measure is equal. In our third step, we can now say that the measure of angle 1 plus the measure of angle 2, so the measure of angle 1 plus the measure of angle 2 is equal to the measure of angle 3 and the measure of angle 4. So this angle is now equal to this angle. We can do that by using the addition property of equality. Step 4, the measure of angle 1 and the measure of angle 2 is equal to the total measure of angle ACB. And the measure of angle 3 and the measure of angle 4 is also equal to the measure of angle PQR. This is the angle addition postulates. In our fifth step, we now take these two angle measures that we just found, the measure of angle ABC and the measure of angle PQR, and because they're both equal to equal angles, they're also equal to each other. So we substitute these two angles, measure of ABC and the measure of PQR, and set them equal to each other using the substitution property. So now we have these two angles, and they are equal to each other. In our last step, we now restate the equality as congruity. So, angle ABC is congruent to angle PQR, and we can state that because of the definition of congruent angles. Let's go back to step 1. We stated congruent angles, and then we stated the measure of equal angles. In 5 and 6, we've reversed that order, and we have equal angles, and then we can state congruent angles. Our next theorem is theorem 2.7.3. This theorem is on the top of page 90 of your book, and it's very small, so you might miss the theorem in your book. What I'd like to do is go ahead and point out the givens for this theorem. It states if two angles, one in each of two pairs of adjacent angles, are congruent, and the larger angles formed are also congruent, then the other two angles are congruent. So it gives us an if-then statement. So if, and let's go ahead and draw these angle notations as they've given it to us. If angle 1 is congruent to angle 3, and angle ABC, so A, B, C, which is the larger angle, is congruent to angle P, Q, R, then consequently angle 2 will be congruent to angle 4. And I just saw something in my notes here that are incorrect. My notes stated that angle 1 was equal to angle 3 and 2 was equal to angle 4. Even the teacher can do this. They are congruent to each other, and now this is the correct notation. So, if two angles, so in this drawing they stated angle 1 and angle 3, one in each of two pairs of adjacent angles. The adjacent angles are angle 1 and 2, and the adjacent angle in this triangle is, this angle is angle 3 and 4. And the larger angles formed are congruent. The larger angles are ABC and PQR. Then the other two angles are congruent. So 2 and 4 are also congruent. This is the same drawing that we just used. So there are many different theorems that you can get from just one drawing. Let's move on to a few definitions from which we'll build our next theorems. We have a linear pair. A linear pair is a pair of adjacent angles whose non-common sides, the non-common sides would be these sides right here. Your common side would be the side in between the angles. So a linear pair is a pair of adjacent angles whose non-common sides form straight angles. So these two sides form a straight angle. Angle 1 and angle 2 form a linear pair. Vertical angles. Vertical angles are a pair of non-adjacent angles formed by two intersecting lines. Angle 2 and angle 4 are vertical angles. However, angle 1 and angle 3 are also vertical angles. So 2 and 4 are vertical, they're across from each other. 1 and 3 are vertical, they are across from each other. You have to be careful with these drawings. It must be 2 straight lines intersecting each other at one point for this definition to work. Two more definitions. Two angles are complementary if the sum of their angles is 90 degrees. So this is two complementary angles. Their sum together equals 90 degrees. 30 plus 60 equals 90. These are also complementary angles. 40 plus 50 equals 90, but they're not adjacent. So complementary angles add up to 90 degrees, but they don't necessarily have to be next to each other. So the word complementary, link it with 90 degrees. Now two angles can be supplementary if their measures is 180 degrees. And supplementary angles can also be adjacent, or they can be not adjacent, but supplementary angles, because they add to 180 degrees, form a straight line. Now, that will only be true if they're adjacent. If they're separated, they'll still be supplementary, but they just will not be adjacent to each other. Our next theorem is the linear pair theorem. And please note, this is two straight lines that intersect each other. Angles that form a linear pair are supplementary. So if you have angles that are together, as an example, angle 7 and angle 8, they form a linear pair. Their non-common sides form a straight angle. So the non-common sides of 7 and 8 are VU and VW. The definition of a straight angle implies that the measure of UVW equals 180 degrees. The definition of a straight angle is 180 degrees, so this implies that these two angles that are supplementary also equal 180 degrees. And the angle addition postulate implies that the measure of angle 7 and the measure of angle 8 will equal this measure of angle UVW. Therefore, the measure of angle 7 and measure of angle 8 equal 180 degrees. So this is an informal proof. We could actually put this in a formal proof table if we wanted to. Basically, what we've done is taken these two steps with the measures of the angles. We substituted 180 degrees for the angle UVW. And consequently, angle 7 and angle 8 must be supplementary because they form a straight angle, and that angle equals 180 degrees. Theorem 2.7.5. If two angles are adjacent and supplementary, then they form a linear pair. So we now have two angles that are adjacent and they're supplementary. They form this angle of 180 degrees. And they are a linear pair. And I wanted to point out that these two angles do not form a linear pair. They are not adjacent to each other. However, they are supplementary because they add to 180 degrees. So make sure that you understand the difference of what a linear pair is. A linear pair will not look like this. Theorem 2.7.6, the vertical angle theorem. This is the theorem for what we've already learned. Given that angle 3 and angle 5 are vertical angles, what we're going to do is we're going to prove that they're congruent to each other. So let's take a look at our formal proof. Here's our picture, and we have angle 3 and angle 5 are vertical angles. That's our given. Our second statement, angle 4 forms a linear pair with both angle 3 and angle 5. So angle 4 forms this linear pair with both of these angles, angle 3 and angle 5. The way that you look at this is you can say that 3 and 4 form this straight line, and 4 and 5 form this almost straight line, form this straight line. We can say this because of the definition of vertical angles that we just learned. Angle 4 is a supplement of both angle 3 and angle 5. So angle 4 is supplementary to angle 3. So that means it's going to add to 180. And it's also supplementary to angle 5. These two, 4 and 5, will also add together to be 180 degrees. In our fourth step, we can now state that they add to 180 degrees. So in step 3, we said they are supplementary because they are linear pairs. Angle 4 is supplementary to both 3 and 5. They are linear pairs. And in step 4, we can now say that measure of angle 3 and the measure of angle 4 equal 180 degrees. That's the definition of supplementary. In step 4, we can also say, besides 3 and 4 being supplementary, we can state that 4 and 5 are supplementary. For step 5, we now state that the measure of angle 3 plus the measure of angle 4 equals the measure of 4 plus the measure of angle 5. So we've taken these two statements, we've now moved one down here, we've moved the second statement down here also, we've set them equal to each other, and we can do that because the transitive property or also the substitution property will work also. So this is the second proof now where we've done this for angles, but we had also done this with segments. And in step 6, the measure of angle 3 equals the measure of angle 5. We are picking these two angles out and their measures. So the measure of angle 3 and the measure of angle 5, because our goal right here, our end goal, is to get to the congruence of those angles. What we've done is algebra, and we subtract the measure of angle 4 from both sides. Now we don't use subtraction property, but we do use addition property of equality. And that gives us measure of angle 3 equals the measure of angle 5. And in our last step, we can state that angle 3 is congruent to angle 5. So we've stated equality. Now we can state congruence. And we state that congruence because of the definition of congruent angles. So, looking on our drawing, angle 3 is congruent to angle 5, and that would mean also that angle 4 is congruent to angle 6. And we already knew that 3 and 5, we stated up here, are supplementary. They form a linear pair, and we use that information to state equality. Our next theorem, Theorem 2.7.7, supplements of congruent angles are congruent. Because of the vertical angle theorem that we just did, we can state that angle 3 is congruent to angle 5 as we did in our theorem, and we can also state that angle 4 is congruent to angle 6. Now we have our first corollary. Corollaries are very interesting. They proceed out of the theorems that they follow. So many times when you do a theorem, it also has other things that will be proved. So in this case, for Theorem 2.77, supplements of the same angle are congruent. This corollary is proved using the same methods as the previous theorem. So supplements of the same angle are congruent. So we would use the same drawing if I said angle 4 has a supplement of angle 3, and it also had a supplement of angle 5, 3 and 5 are congruent. Theorem 2.7.8. Complements of congruent angles are congruent. Complements of congruent angles are congruent. So both angle 3 and angle 2 and angle 3 are complementary to angle 1. Complementary means that they add to 90 degrees. Therefore, angle 2 and angle 3 are congruent. Let me give you an example. If angle 2 was 45 degrees, and it was complementary to angle 1, that would make angle 1 45 degrees. Angle 2 and 3 are congruent because they're both being added to angle 1 of 45 degrees. Theorem 2.7.9. All right angles are congruent. Angle 1 and angle 2 are congruent because right angles are congruent to each other. All right angles, remember, are 90 degrees. The measurement of one right angle will be congruent, or will be equal to the measure of another right angle, and they will be congruent to each other. Theorem 2.7.10. Congruent supplementary angles are right angles. So if you have congruent angles, which are going to have the same measure, and they're supplementary, which means they have to add to 180 degrees, then both of those angles would have to be 90 degrees each. 180 divided by 2 would be 90. Theorem 2.7.11. If one angle of a linear pair is a right angle, then the other also has to be a right angle. So I have a linear pair, angle 7 and 8. if angle 8 is a right angle. And let's go ahead and draw that in there. If angle 8 is a right angle, looking at these angles up here, you can see that angle 7 would also have to be a right angle. And consequently, for angles 7 and 9, they would both have to be right angles, and these two angles would also be right angles. I realize this is quite a few theorems and definitions for this one lesson. So just make sure that you have updated your list of definitions, postulates, and theorems. Make sure that, particularly with the theorems, that you have drawings next to them so you can use them when you're doing proofs. And then for the next video, we will go over the homework for this lesson.